Hello, my name is Marie-Helene Hamon. I'm a research program manager in Orange Innovation, and I'm going to present you the view from an operator on 6G requirements and some of the key technical challenges that we see ahead of us. Activity has been ramping up on 6G for the past months and years. Quoting some of the initiatives, it started with activities such as the 6G flagship program in Finland, launched in 2018, or the organization of dedicated conferences such as the 6G Wireless Summit from 2019. In Europe, there has been a start of dedicated project with the flagship project ExaX, which started at the beginning of this year, and more projects will come in the coming months and years with the new program Smart Networks and Services. In Asia, there has been the launch of several national R&D programs on 6G in Japan, in China, and in Korea. And in the US, there has been the early white papers from academia, such as the Virginia Tech white paper in 2019, the opening of spectrum in the terrestrial band by the FCC, and more recently, the launch of new alliance, the NextG Alliance, and a new series of symposium, the TGC Symposium, at the October of last year. At the international level, the work has started in ITU, and the Future Technology Trends report is expected by mid of next year. And in NGMN, a 6G project has kicked off in October 2020. In Orange, we are participating to some of these initiatives, such as the ExaX project, and we are also following the work in ITU and the 6G project in NGMN, and also we participate to the ION Global Forum, which was launched by Intel, NTT, and Sony, and which also focus on fixed network. So we are at the beginning discussing about the use case and requirements for 6G, and we believe that we need to take into account in the definition of the requirement for 6G the framework which has been set by the United Nations on sustainability. They have defined 17 sustainability development goals which stress the importance of some research direction for 6G, such as the minimization of the energy consumptions, which should be performed with an end-to-end perspective. And with 6G, we should not see additional energy consumption, even though the traffic keeps growing. We should also aim at minimizing the environmental impact at all levels, from the core network to the terminal, and at all phases. So from the beginning, the design, the manufacturing, to the usage phase, and up to the recycling of the equipment. Another important direction is digital inclusions, which should be improved. So 6G should really aim at improving the coverage in areas which are currently not very well served. And 6G should also target affordable costs to enable economically viable deployment in low-income areas. So these are the directions which are part of Orange commitment in our strategic plan Engage 2025. We are at the beginning of the definition of 6G, discussing about the use cases and the requirements for 6G, and there's already been a lot of publications setting performance target for 6G, which has much beyond what can be achieved with 5G, so higher capacity, higher data rates, lower latencies. But we believe that we need to define, alongside this performance requirement, societal requirements to be considered and treated with equal importance as these performance requirements. So some example of what could be this societal requirement, it could be the energy efficiency, which should be much improved with respect to 5G, with gain which could be similar to what we are expecting for capacity gains. It should also be the low end-to-end environmental impact, which should be taken into with much higher importance than it is with 5G. Security should be higher, resilience should be much higher, digital inclusion should be improved, both in the direction of affordability and of coverage of low-density areas, and EMF awareness should be higher. These societal requirements need to be defined, and we need also to define corresponding target values for these requirements. So there's also currently a lot of discussions on the use cases and applications for 6G. So just quoting a few of them, there is a generalization of higher definition multimedia with 64K, which will set tight constraints on the capacity, the advanced industrial and robotics applications, which will be really demanding in reliability, latency, the communication for the AI and the communication of the five senses, where we will transmit more than the image and the voice, but also other senses like touching. And there is already a lot of work on the 6G possible technology enablers or disruptions, and quoting a few of them, there is, for example, the terrestrial spectrum, the use of high frequency bands, the radio sensing and imaging, the energy-free devices, the reconfigurable intelligent surfaces, or the use of artificial intelligence at all the network levels, and including the physical layer. So this is not meant at all to be exhaustive, it's just a few of the technologies that we are looking more specifically. And this technology are promising, but set also very tight challenges, and this what I'm going to discuss just after. The first technology disruption is the use of high frequency bands. They are interesting for capacity demanding applications such as telepresence or holograms, because going higher in frequency, we can expect higher spectral availability than in the lower bands. They are also interesting for applications such as localization and sensing. So there are currently a lot of work on the bands above 100 GHz, so either in the band between 100 and 300 GHz, the sub-terahertz or upper millimeter wave bands, or even the terahertz bands above 300 GHz. But use of these bands set also a lot of key challenges. The first one is the characterization of the propagation. We will have, as we have with millimeter wave bands, blockade situation or non-line of sight situations, which could lead to a loss of service. We will also see higher path loss, which we call for higher gain antennas, and high diffraction loss and material loss. So we need to conduct measurements and characterize all of this. Antenna is also another challenge, because designing high gain antennas at such frequency would require very large antenna apertures. We will also need new antenna architectures, because the current antenna architectures will not scale easily with the frequencies. And we will also have to face more impairments in the implementation process. And implementation is a global issue also at these bands, because hardware implementations is a challenge, and we need to define what will be the semiconductor technology for those bands, and what will be the maturity and the cost. When will we have product for the mass market is a key question. Another technology enabler are the reconfigurable intelligent surfaces. They are interesting because they enable to control the wireless propagation environment by reflecting the signal and without generating new signals, so they can be a tool to improve the EMF awareness. They can improve the performance by, for example, assisting the beamforming or reducing the interference. But they also set tight challenges, such as we need to characterize their performance and see how we can integrate them into the network. So we need solution to control the surfaces according to the trade-off that we will set between performance, EMF awareness, or any other target that we define. We also need to find new network architectures to integrate these surfaces. Another important issue is the coexistence. We need to avoid a situation where the reconfigurable intelligent surface from one operator to degrade the network of another operator, because it could generate unwanted reflection. So we need to assess this coexistence issue and potentially define coexistence technique to address it. And we also need to look at how we can regulate the deployments. So this is an issue we are looking at in range with a first prototype. Zero energy devices represent another interesting solution, in particular with respect to the sustainability targets. So they will rely on harvesting of energy, such as solar energy, and harvesting of electromagnetic waves. So they will not emit new waves, but they will reuse the existing electromagnetic wave, which are sent from a source, such as base station, to a terminal. and they will reuse it to send a short message. So they are interesting for IoT applications and for battery limited devices such as sensors, and it can be all the more interesting if we see a generalization of the sensors in the 6G use cases. But there are also very many challenges associated with the use of these devices. First is they will suffer from poor performance because the backscatter link is a low power link and it will suffer from the interference from the source signal. So we need solution to improve this link, otherwise we may have a loss of service. And another challenge is that we need to design and to integrate this device in the network while still being compatible with the sustainability target. So we need to avoid deploying specific sensors for this, but reuse as much as possible the existing device or the already deployed equipment and integrate these tags into this existing equipment. And we need to target full energy autonomy or almost. Last, machine learning is a key enabler for 6G, and we are looking here more specifically at the machine learning driven 6G air interface. So machine learning is a powerful tool to model and optimize, and it can be applied to the air interface. So we can use, for example, the machine learning parametric models to capture complex physical phenomena, such as, for example, the channel propagation or the hardware impairment we were discussing just before about these challenges for terrestrial bands, and machine learning may help here. And machine learning algorithms are interesting to solve the hard to optimize problems, such as, for example, when we have to deal with complex constraints, such as the power consumption or the fairness. And we also have the online learning strategies to adapt to the network dynamicity, such as a change in the traffic load or the default on equipment. But there are different challenges to be addressed to use machine learning for the air interface, such as the energy efficiency. We need to be careful that the computational cost, the hardware complexity, and the power consumptions due to the inference and training phases do not compensate the gains that we are targeting with the use of machine learning. We also need to have scalability and sustainability, so we need to be flexible and be able to adjust to new architecture. We need to have explainability and trustworthiness. We need to be able to understand the optimization which has been done by the machine learning. We need to be sure about the data that we will use for the training and the validation. So we need to be careful about the origin of this data, the quality of the data, the freshness, and what it will cost to acquire this data. We need to be careful also about the security. We need to be resilient against attacks. And a key question is the standardization, so how we will standardize the learning procedures and protocols. So there are several challenges ahead, and this was not meant to be exhaustive. It's just a few ones that we are looking at. And the work is underway to address this in various entities and bodies. So in conclusions, we stress that we need to define the societal requirement for 6G in addition to the performance requirement, and we need to do it now when we start designing the system. And we participate in various entities and bodies such as NGMN or ION or collaborative projects to address this. And we need technical solutions to meet this performance requirement and these societal requirements. And we participate on this topic to European collaborative projects such as the flagship project ExaX, which will define the vision for 6G and working on the technology enablers, and the RISE 6G project, which is more specific to the reconfigurable intelligent surfaces. Thanks for listening to me, and I will be happy to take questions.